All right, so today we're going to do some chemistry review of all the chemistry concepts we've learned in Science 9. Again, the reason for this is I'm trying to prepare you for the things that you need to understand going into Science 10. So these are going to be the basic understandings from chemistry in Science 9 that'll help you succeed in Science 10. Here we go. So again, we're going to focus on those outcomes I just mentioned. Just a bit of a heads up, you're going to want to have a periodic table all ready to go today. I know I gave them to you earlier in the year. If you want to have a look through your binder and find it right now, might as well just pause the video and go find it. That's great. But if you don't think you have it, or if you just want to go looking for it, that's fine. A digital periodic table is posted on Google Classroom underneath Final Review. It's in there somewhere. You'll just have to find it. And you can have that open on another screen if possible, or at least just understand you can pause and then go find it from there. As we go through this lesson, just by the way, to save you some time, like it's just really important that you can do this, just to save yourself any trouble. On your Science 10 cheat sheet that's going to be due later this week, you can fill in notes as this video goes on. The information in this video is everything that you need to know from the chemistry unit. You don't have to add any other information if you don't want to. You can just stick to what I'm going to talk about in this video and throw that on there right now. Now, it's ideal for you to put things in your own words, but if you're more comfortable just copying this as notes and putting on there, feel free, right? If that's at least the least you can do, go for it, right? Just another thing to say with chemistry in particular, putting examples and their solutions, which we're going to do today, on your cheat sheet would be a great idea, because oftentimes an example will say a lot more or show a lot more of the process than just giving a definition would, right? So that'll be really important to throw on there. And again, just to make it really clear, if I haven't made it clear already, the purpose of the Science 10 cheat sheet is so that you have something going into Science 10. Like you can keep this thing safe, and then once you go to Science 10, you can bring this out and be like, okay, boom, I just have one page, one side on a page that I can look at in one single glance and go, oh, that's how we did that, right? So you won't have to worry about stumbling and going, oh, I can't remember how to do this. You'll have it right there. This is going to save you so much trouble in the long run. Anyway, I'm going to stop rambling. Let's get going. It might be a bit of a long lesson today. I apologize. Chemistry was the biggest part of Science 9, so we'll see. Anyway, here's just a reminder of where everything fits. We're focusing in on chemistry today, which is, of course, one of the three main units of Science 10. The stuff from Science 9 that leads into it is environmental chemistry, but more significantly, matter and chemical change, which was so much chemistry that I actually literally just called it the chemistry unit of Science 9. Anyway, let's move on. So the chemistry concepts you need, I think I've shared this with you before. It's going to be the Wimmis symbols. We'll go over that real quick. At very least, you just have to know what they are and what some safety procedures you'd have to use when you deal with things that have certain Wimmis symbols. Ionic compounds, which is a metal and a non-metal, which includes naming them and making their formulas. That's huge. Another thing that is equally huge is molecular compounds, which is where you have a non-metal and a non-metal. And once again, it's naming them and making their formulas. That right there is like the single most important skill from Science 9 of any topic that you'll need going forward. So you absolutely need to make sure you've got that mastered. Another thing you should really have a good understanding of that we'll talk about today is how do we know a chemical reaction has actually occurred. And then the last thing we'll talk about are acids and bases, which includes their pH, of course, as well as litmus paper and stuff like that, as you can see in this picture. Anyway, moving on. All right, Wimmis symbols. There was 10 of them under the 2015 system that you need to understand and recognize. Remember, Wimmis stands for Workplace Hazardous Materials Information System. They appear on chemical containers to provide information as to the dangers they pose. If you're going to put this on your cheat sheet, you can basically just say, know your Wimmis symbols, maybe even draw like just small pictograms of some of the ones that you might not remember so well. I know this one right here where it's a flame over a circle can confuse some people. This does not mean flammable. Flammable is just the flame by itself on like a solid surface. A flame over a circle means it's for oxidizing hazards. Oxidizing hazards are things that react with oxygen that can light on fire, but again, the whole idea is it'll react with oxygen in the air and react that way, right? Oxidization reactions aren't always a big flame, right? So this picture is just a little, I don't want to say misleading, but it's maybe over exaggeration. Oxidizing is what makes iron turn into rust, for instance, right? It's an oxidizing reaction. So it's kind of like burning, but very slow, but still, that's the idea. Another one that really always stumbles people is this health hazard one right down here, where it shows like a silhouette of something and someone, and then like something's like blowing up inside of them. Those are the kind of things that could cause serious long-term health effects, right? So in other words, you know, something that might be cancerous, that would be a health hazard like this, right? An exclamation mark are less serious health effects. So again, you know, it could cause just illness breathing it in, but it's less serious than this one. These two kind of go hand in hand, but this one's a little bit less serious, despite the fact that there's an exclamation mark, which is interesting. The one that you don't really need to know too much of is this biohazard one. In chemistry, we don't really deal with biohazards too much, but it is important to understand that it's still a thing that exists. Anyway, moving on. All right, next thing that we need to talk about, just kind of a lead-in before we talk about ionic and molecular compounds, is the periodic table. So hopefully you have one in front of you. If you're glancing at it right now, that's great. Keep in mind your periodic table of elements lists all the elements that make up what we call matter. So all like actual physical things. Now all matter is made up of these elements or combinations of these elements. A combination is called a compound. We'll get into that in a little bit here. Now one individual particle of matter is of course called an atom. Atoms are made up of protons, which have a positive charge, neutrons, which have no charge, and electrons, which have negative charge. We'll go into more detail on this when we get into our physics section in a couple days. But the number of protons is actually what determines what type of element it is, right? Now, the number of protons for an element cannot change. If it changed, then your element itself would change. It would no longer be carbon, for instance, right? Protons are found in the center, or in other words, the nucleus of the atom. Neutrons are also found in the nucleus of an atom. They don't have a charge, though. And then electrons are the ones that are orbiting around it. Now, electrons, generally speaking, you have the same number of electrons as you have protons. But if your atom has an electric charge, then your number of electrons will be different. An electric charge, look at the word elect, right? In that elect, it's like electron, right? An electric charge is determined by whether you have more or less electrons than you should, right? That's basically how it comes. Anyway, moving on. So this is, of course, what your periodic table looks like. This is the exact kind of one that I printed off for you guys. What's important to understand right now is it's color-coded for a reason. Anything that's green is a metal, okay? So most of the stuff on the periodic table are metals. Anything that's this purple color, those are metalloids. They're kind of like an in-between between a metal and a non-metal. We don't need to worry about those too much. But anything that's this like orangey salmon kind of color, that's a non-metal. And for the most part, they're on the right-hand side of the periodic table, but of course, hydrogen's way over here on the far left. But still, those are your non-metals, and they would make up what we call molecular compounds. Anyway, moving on. So ions is another thing we got to talk about. An atom that has an electric charge will either have more or less electrons than it has protons. Now, charged atoms are called ions. So as soon as an atom gets an electric charge, we don't call it an atom anymore, we call it an ion. Now, if it has more electrons, so if it gained some electrons, that means it's going to have a negative charge because electrons, of course, carry negative charges. More electrons is a negative charge, and we call that an anion. I always thought that kind of sound like onions, and onions smell bad, so they're negative, right? So anion, negative. Less electrons, however, so if it gave away some of its electrons, that means it's going to have a positive charge. And a positive charge is called a cation. And I always thought of that because positive kind of sounds like pause, and cats have paws, right? Now, different elements will have different preferred ionic charges. The preferred charge is listed on the periodic table. It's kind of up in the top corner. Some elements actually have more than one preferred charge, and they can exist as either one. We call those multivalent, and they're very important to recognize and consider when dealing with ionic compounds, which we'll deal with in just a second here. So on the periodic table, of course, every single element has a little box that looks like this. So this one, of course, is for oxygen. We've got this one labeled. Some of the important things to understand here is this atomic number in the top corner. That tells you how many protons you have. Okay, so this top number is your number of protons. This number at the bottom is your atomic mass. That's equal to your protons plus your neutrons, right? So in other words, if you wanted to find how many neutrons you have, you just take this number and minus this number. So for oxygen, coincidentally, it has the same number of protons and neutrons. Not every element is like that, though. You gotta be careful. Now up here in the top right-hand corner, that's your ion charge. So if oxygen is going to be charged, it's gonna have a -2 charge, right? That's just how it wants to exist. It likes having a -2 charge. So if it's going to get a charge, it's gonna be -2. And -2 means it gained 2 electrons. Now I know negative is kind of backwards to gain, like you think gain would be a positive, but no, because we're dealing with electrons, a -2 charge means you actually gained 2 electrons. So if you had an oxygen, ion, then that thing would have 8 protons 8 neutrons. Those don't really change. Neutrons can change, but you won't deal with that until you're like in physics 30, so don't worry about that. But your number of electrons, if it was an oxygen ion, is going to be 2 more than the number of protons, so it would have 10 electrons. 8 plus 2, of course, being 10. If it was an oxygen atom, then you'd have 8 protons, 8 neutrons, and also 8 electrons, because those two would have to match if it was an atom. Okay? Anyway, moving on. All right, here's where it gets really important. Okay, so you'll really want to focus in on this. Ionic compounds. When elements combine together, they form compounds. Compounds are just where you have more than one element mixed together. Compounds can be classified as either being ionic or molecular. We're going to deal with ionic first, okay? Ionic compounds, generally speaking, not always, but almost always, like 99% of the time, in every case we're going to look at least in Science 9, ionic compounds contain a metal and a non-metal, okay? Now, metals will always serve as a cation, so they'll always be the positive one. Non-metals are always going to serve as an anion, so they'll be the negative one, okay? The total sum of all the charges in an ionic compound must always equal 0, right? So if you look at your periodic table and see what your charge is on your metal and what your charge is on your non-metal, and then you look at how many metals and non-metals you have, and then you add it all up, it should always equal 0. It has to balance out. Now, when given the formula for an ionic compound, so if I gave you a formula, naming it actually isn't too bad. So if I gave you the chemical formula for an ionic compound, which we'll deal with in just a second, naming it's not too bad. All you have to do is you write the name of the metal first. So if it was iron first, you just say iron. Then you look if the metal has more than one possible charge. Usually it doesn't, so usually you can skip this step. But if it has more than one possible charge, you have to determine what charge it has. We'll get into that in a second. And write it in brackets after the metal name using Roman numerals. This step doesn't always get done because, again, most charges on the periodic table, most elements on the periodic table only have one charge, right? So most of the time you don't have to do this one. So usually you can just skip right to 3. Step 3 is write the non-metal name, but just change the ending of it to IDE, I-D-E, right? Let's see a few examples because I think examples are going to go a long way here. And examples are going to be useful for writing on your cheat sheet. This right here, by the way, these 3 steps, and as well as, of course, the description saying what you're actually doing, that would be really, 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 really important to put on your cheat sheet. Like, I cannot even express how important that is right there. So you'll really want to jot that down. Anyway, let's do some examples. You'll want to put these on your cheat sheet as well. MgO. I'm going to be honest here. I'm going to need to get a periodic table handy. Look at me go. I'm kind of being a bit of a hypocrite. I don't have one. But MgO, I know magnesium is Mg, and O is oxygen. And I actually know, without even having my periodic table open quite yet, that magnesium only has one possible charge. So all we have to do is write the metal name first. Magnesium. Oops, it's not letting me write. Here we go. Magnesium. There's no Roman numerals because it only has one possible charge. And then oxygen is my non-metal, but remember you got to change the ending to "ide." So it's going to be oxide, right? It's not going to be oxygenide. It's going to be oxide. Sometimes you just have to know which one is which. It's not really an exact rule all the time, but it's just, yeah, you'll have to just know based on what you're dealing with. Anyway, we're moving on to the next one. Next one, Ca3P2. So you got 3 of these guys and 2 of these guys. Well, the numbers don't actually really make a difference in terms of what the ionic name is, unless, of course, that your metal has more than one possible charge. Well, our metal in this case is Ca. Ca, if you look at your periodic table, that's calcium. Calcium only has one possible charge, right? So in other words, we're not going to have to worry about our Roman numerals. So we literally can just call this calcium. And then the P, of course, P is phosphorus. So that's going to become phosphide, right? Calcium phosphide is this guy right here. Remember, the numbers here just tell you how many of each you have, right? It doesn't actually make its way into the name for an ionic compound. It just tells you how many of each of those atoms you have, or ions, I guess I should say that you have. And just to go back to that whole math thing about how it has to equal 0, calcium, if you look at your periodic table, has a +2 charge. And phosphorus, if you look at your periodic table, has a -3 charge. Since there's 3 calciums, 3 times 2 positive is 6 positive. And since there's 2 phosphorus, 2 times -3 is -6. Well, +6 and -6, that cancels out to be 0. So this one is actually properly balanced. We're going to do this last one here, PbO2. Notice the lowercase here on the B. Like, I know it's kind of weird having P and B. That means this is your metal, right? So that's the one thing. And the next time you see a capital letter, That's your next one. So that's your nonmetal. Well, PB, you're going to have to scan your formula sheet for this one. That's lead, right? So lead is your metal. But unfortunately, when you look at lead on your periodic table, you'll see it actually has more than one possible charge. So now you have a little bit of work to do. Lead could either be a +2 charge or a +4 charge. And we need to figure out which one it is. To figure out which one it is, you have to look at your nonmetal first and figure out what your total charge is on that. There's 2 oxygens here. Oxygen on your periodic table has a 2 negative charge, but you have 2 of them, so that means oxygen in total here has a 4 negative charge. Notice you only have 1 lead. That means this 1 lead has to counteract this -4 charge, so this 1 lead has to have a +4 charge. Since it has a +4 charge, we now know which type of ion it is. And because lead could have either a +2 or a +4 charge, we have to indicate it in the name. It has a +4 charge, so you write it with Roman numerals. 4 in Roman numerals is like an I and a V, so it's lead 4 oxide. That would be the name of this guy right here. I want to make it very clear, I'll just erase this. I want to make it very clear that this Roman numeral does not tell you how many leads you have. It only tells you what the charge on the lead is, okay? So don't confuse that for how many leads you have. All right, moving on. All right, now writing formulas for ionic compounds. When you're given the name of an ionic compound, you need to check the charges on your periodic table. You'll need to mathematically determine the lowest multiple of each one, blah, blah, blah. That's hard. The easier way of doing this is to use a method called swap and drop. Find the charges on each one, swap them, and then drop the number to the bottom right corner, okay? Now, if there is a number after you do this that can divide both of those charge numbers, well then divide it so you reduce it to lower terms. This is a lot easier to see when you see some examples. It sounds awful when I write it out like this, but when you see some examples, it becomes way easier to do. So here's the first one, aluminum phosphide. What you do is you got to look for your charges on both these first. So if you look at your formula sheet and you find aluminum, it takes a little bit of time sometimes, but you find it, you'll see it has a +3 charge. Phosphorus, on the other hand, so phosphide, phosphorus has a -3 charge. Now, to some of you, it might be clear right off the bat that these already balance out, so you only need one of them. But if it wasn't clear to you, you can use the swap and drop method. So swap the 2 numbers, 3 and 3, and then drop them to the bottom corner. So aluminum, which is Al, is going to get a 3 down here, and phosphorus, which is P, is also going to get a 3. But notice you can divide both of these numbers by 3. In other words, you could reduce it, kind of like reducing a fraction. Since you can divide both of them by 3, do that. Divide both of them by 3. So 3 divided by 3 is 1, so really we just have aluminum, just one of them, you don't even have to write the 1 there, and phosphorus. So ALP, that would be your answer right there, and that is now completely balanced. Let's do another one. Sodium sulfide. Sodium on your formula sheet, on your periodic table, has a +1 charge. Sulfur, which is your sulfide here, sulfur has a 2 negative charge. Okay, so this is where swap and drop is really going to become useful. Swap the numbers and drop them. Sodium is Na. It's going to get a 2, and then sulfur is an S. It's going to get a 1. You don't have to write the 1, right? If you're ever not sure whether or not this works, check your charges again. Sodium has a +1 charge. 2 times +1 is +2. Sulfur has a -2 charge. There's only one of them, so that has 2 negative. It balances out. It's equal to 0. We're good to go. And there's nothing we can divide both these numbers by. Didn't mean to put a little slash there. There's nothing we can divide both those numbers by, so we're good to go on that one. All right, last one here, cobalt-3 oxide. This is nice. When you go the other way around, this is nice having your Roman numeral already set and ready to go because it tells you which version of cobalt to use. If you looked at your periodic table, you'd see cobalt could either have a 2 positive charge or a 3 positive charge, but it's already told us this one's going to have a 3 positive charge. That's awesome. Oxygen, however, only has a 2 negative charge. Swap and drop them. Okay, so cobalt is CO. It's going to have 2 because you swapped them and you dropped them, right? And then oxygen is going to have 3 because you swap and drop, right? Got the 3 from the cobalt. If you're ever not sure, double check. 2 times +3 is 6 positive. 3 times -2 is 6 negative. They balance out. We're good to go. And there's nothing that you can divide both those numbers by, so we know we were good to go there. All right, we're almost done here, don't worry. Molecular compounds. Molecular compounds, I gotta be honest with you, are for most people a little easier than ionic compounds. So it was nice to deal with a hard one first. These ones are usually a little easier. Molecular compounds, unlike ionic compounds, don't care about charges. You don't have to look at the charge for molecular compounds. Charges don't play a role here. However, something that didn't matter for ionic compounds but does matter for molecular compounds is the number of each element in them. Now we use prefixes, these things right here, so words that kind of just like go before your word, to communicate what number each of these have. Mono is for 1, di is for 2, tri is for 3, tetra is for 4, and so on. Really, you only need to know the first 6, at least for Science 9. For Science 10, you'll go all the way up to 10 for sure, but at least know the first 6. Note, however, if your first element only has 1 atom, you don't actually write the mono for it. Mono is only used when the second atom only has 1, right? So a very classic example, and hopefully I don't have it on another slide. I can't actually remember what my examples are, but a very classic example is CO, right? That's carbon monoxide, right? Carbon is a nonmetal, oxygen's a nonmetal, that's why this is molecular. We write that as carbon monoxide. We don't write it as monocarbon monoxide because mono is only used for the second one. Now, if you had 2 carbons, you would call it dicarbon monoxide, right? These other ones can be used for the first element. It's just mono for whatever reason. If there's only one of the first one, we don't put it on the first one. It's just convention. We don't call it monocarbon monoxide. We just call it carbon monoxide. Okay, moving on. All right, so here's some examples. Look, carbon monoxide is in that list. That's kind of funny, but hey, you know what? We'll go over it anyway. First one here, 1 carbon, 2 oxygens. Well, that would be carbon, because there's just one of them, so we don't put monocarbon first. Mono only goes on the second one. Carbon, and then you get 2 oxygens, that's dioxide, right? Notice we're still ending with "ide", just like what we did with ionic compounds. I don't think I mentioned that, but just make sure you're doing that. Next one, 1 carbon, 1 oxygen. Like I said before, that's carbon monoxide. No problem there. N2O3. Well, that's nitrogen, and there's 2 of them, so we call that dinitrogen. And then 3 oxygens, that's trioxide. So it's dinitrogen trioxide. What about this one? 1P. Well, P is phosphorus, so we won't write monophosphorus. We'll just call it phosphorus. And then we got 5 Fs. Well, F is fluorine. 5 means penta, so pentafluoride, right? Not pentafluorine, it's pentafluoride. Last one here, H2O. That one's kind of a joke. You'd say water, right? Like honestly, that's water. But if you wanted to give it a proper molecular name, because hydrogen and oxygen are both nonmetals, well then by our naming conventions, we would say that this is because there's 2 of them, dihydrogen, and then 1 oxygen would be monoxide. So dihydrogen monoxide is a really fancy way of saying water. Okay, anyway, moving on. All right, formulas for molecular compounds. It's the same process, just in reverse. So you use your prefixes to determine how many elements you have. The hardest part's usually just determining the atomic symbol for some of the more obscure elements. That's about it. So just use your periodic table wisely, look for the thing, and go from there. Anyway, here's some examples. Silicon dioxide. By its name, we know we only have 1 silicon and 2 oxygens. Silicon is Si. It's a metalloid, but metalloids usually count as nonmetals. Si, and then dioxide, there's going to be 2 oxygens. Okay, so SiO2. Next one, dinitrogen pentoxide. Notice it's not pentaoxide. Sometimes they just put the 2 vowels together and just make it 1. There's no rhyme or reason to it. I never mark you as being wrong if you didn't put that in right, but whatever. Dinitrogen pentoxide, di means 2, so N2. Pentoxide is O, and pent is 5, so O5, N2O5. Next one, tetraarsenic. Notice this time they didn't combine the vowels. That's kind of interesting, whatever. Tetraarsenic decoxide. Well, this is kind of unfair because we don't usually use the dec one too much, but it's good to know either way. Arsenic, first of all, arsenic is As. Tetra means there's 4 of them, so As4. Dec actually means 10. So 10 oxygens, so O10. There you go. Again, you only need to know up to hexa, which is 6. But sometimes it's nice to play around with the bigger ones too. Whatever, no big deal. All right, chemical reactions. We're in the clear here. There's no more real calculations to do or anything. A chemical reaction is when elements and or compounds react to form something new. The elements in a reaction don't change. No elements just come out of thin air. You can't just make that, right? Well, you sort of can. You'll deal with that in physics 30. But for now, you can't just make elements out of thin air. They attach to different elements or break apart. So in other words, if you're doing a chemical reaction, if gold, for example, wasn't something that went into the chemical reaction, whether on its own or whether it was part of a compound that contained gold, gold will not be something that comes out of a chemical reaction. Alchemy is not a thing. Alchemy is the old science study that they did way back in the Middle Ages where they're like, oh, we can make gold out of nothing. No, you can't. Chemistry proves that alchemy is not a thing. You can't make gold out of nothing. Gold has to be coming from something else first, right? So the elements on the periodic table are not going to change. They're just going to change what they're bound to. That's it, okay? Now, a chemical reaction may have occurred if we see any of the following things. This isn't a surefire way of proving it, but at least is a way of us suspecting that a chemical reaction has occurred. If there's a color change, there's a decent chance that a chemical reaction has occurred. Now, of course, one exception to this would be like if you put Kool-Aid mix in water. So if you had your water and you put some Kool-Aid mix in there, there's no chemical reaction that occurs. It's just your Kool-Aid mix, which let's say is blue or something, is mixing in with the water. Okay, so not always, but you know, it can be a good indication. An odor being released, that is a good indication of a chemical reaction. For instance, if you had like some fruit that was going rotten, that rotting is a chemical reaction, and that smell is an odor being released from it. Formation of a precipitate. Precipitate is a solid, or when the solution goes cloudy. That's another way of saying, yeah, it probably was a chemical reaction. So if you mix two things together and like a solid chunk thing formed after that, probably a chemical reaction occurred. A release or an absorption of heat, that's a very good indication that a chemical reaction occurred. If you mix two things together and all of a sudden it's warm, yeah, it was probably a chemical reaction occurred. You might remember the elephant toothpaste thing we did, where we mixed, it was like a yeast solution and hydrogen peroxide. And then we even put some dish soap in there just so it wouldn't smell terrible. That released a lot of heat. It was very warm after that. So that told us that there was a chemical reaction that occurred. And then another one, gas being released, or in other words, bubbles formed, or like in this crazy picture, there's like some gas coming off this. A chemical reaction probably occurred. Now, of course, an exception to that would be if you had a pot on the stove and you boiled your water and there's bubbles coming up, right? No, that is not a chemical reaction. You're just heating water, so it goes from a liquid to a gas. That's not a chemical reaction. But again, these can be used to determine whether or not it occurred. Last thing we're going to cover here is acids and bases. I want you to know that acids have pH less than 7, and that they act as electrolytes. We learned about that in our electricity unit. Remember, we talked about car batteries having an electrolyte in them, and it usually was like battery acid, right? So they help conduct electricity in a solution. And another thing I want you to really know is that acids turn litmus paper red, okay? Those are the only things that you really, really need to know. But yeah, it's good. Anyway, bases, number one thing you need to know about a base is it has a pH more than 7. They can act as an electrolyte as well, but they're not not typically, I should say, as good of an electrolyte as an acid. They'll get into that later, though. Another thing I want you to know, though, is it turns litmus paper blue. Okay, that's a base. Neutral things have a pH of exactly 7. They can be an electrolyte, but they could also not be an electrolyte, and they have no effect on litmus paper. Regardless of whether you had red or blue litmus paper, neutral aren't going to do nothing to it, right? So in other words, neutral things don't have an effect on litmus paper. They have a pH of exactly 7. Best example of something that's neutral is water. Pure distilled water is neutral. Anyway, so your task now, we're done for today. Your task now is I want you to take your cheat sheet, which might look something like this. You can do it in different ways if you want, but it might look something like this. And I want you to make sure that you have your notes filled in under chemistry, right? Everything we've talked about today is important for going forward and succeeding in Science 10. But if there was a number one thing for you to know, it's how to name and write the formula for ionic compounds, and how to name and write the formula for molecular compounds. Anyway, if you haven't already done that as watching through this video here today, that's your only task now. But if you were following my initial direction and you were filling this in as you went, you're good to go. Sorry for a long video today, guys. That was almost half an hour long, but again, chemistry was a big part of this. I doubt the next 2 videos are going to be as long. Watch as I eat my words, though, but I don't think they will be. Anyway, best of luck. If you need anything, please send me an email.